In this video, we'll talk about the spin-orbit correction to the hydrogen atom. We'll start with the electron classical gyromagnetic ratio, then the quantum gyromagnetic ratio, then introduce and solve the spin-orbit correction, and finally put everything together to calculate the fine structure for the hydrogen atom. We start by taking a look at how the proton sees the hydrogen atom. The proton is more or less fixed in space. The electron is orbiting around that proton. And in a classical way, we can treat it as taking an orbit around, in a circular orbit around the proton. And therefore, the electron has angular momentum about the proton. If we look at the electron's perspective, however, in the electron's frame of reference, it's the opposite. That is, the proton has angular momentum about the electron. And since the proton is charged, it not only generates an angular momentum, but also a magnetic field. So the rotating proton has an angular momentum L, and it produces a magnetic field at the position of the electron, which we'll call B. The magnetic field then interacts with the electron magnetic moment and produces a torque and changes the energy because there's a perturbative energy effect on the magnetic moment of the electron. The Hamiltonian for that is minus mu dot B, where this is the magnetic moment of the electron. This is the magnetic field that the electron perceives. We can generate that field and calculate it using the Biot-Savart law, which says that the magnetic field is just the current divided by 2r times the permeability of free space. That can be rewritten as mu naught is 1 over epsilon naught c squared, so you can rewrite B as I over 2 epsilon naught c squared times r. You can then substitute in for the current by assuming that you have an electron or a proton with charge E rotating in a time tau around the orbit. And that means your current is just the total charge E divided by the time tau. The angular momentum is simply the radius of the orbit times mv. V is just the circumference, 2 pi r over tau. And so this becomes 2 pi mr squared over tau. If you then combine this quantity for L, this expression for L, with the magnetic field, you can rewrite the magnetic field as the following. You can eliminate tau and get that B is equal to 1 over 4 pi epsilon naught E over mc squared r cubed times L vector. Because B and L are in the same direction, there's a positive sign to this. So this is an expression for the magnetic field that the electron sees due to the proton. The electron has a magnetic moment. So classically, we'd like to calculate that electron magnetic moment. And we do that by taking literally this idea of spin. Let's assume that the electron has it can be represented by a loop of charge, a ring of charge Q, and a mass m rotating about its axis with a period tau. So the same period. So that electron's rotating on its own axis, and we can sort of draw it like this. This is the ring of charge that represents the electron charge. It's spinning about its axis. That produces a momentum and a magnetic moment. So the magnetic moment is simply the current times the area of the loop. Well, the area of the loop is pi r squared, and the current is a total charge Q passing through a particular point in a time tau. So mu is equal to I times A, I being Q over t tau, and A being pi r squared. So S, this spin angular momentum for this classical electron, is just the moment of inertia times the angular velocity. So if we're assuming that this is a ring of charge with mass m, then the moment of inertia I, capital I, times omega is equal to s. And that can be rewritten with omega as being 2 pi over tau, and I being mr squared, moment of inertia of a ring. So the gyromagnetic ratio, gamma classical, is simply the ratio of the two quantities that we've calculated. That is mu over s. So gamma classical is equal to mu over s. We can take these two expressions, put them in. We get q pi r squared over tau times tau over 2 pi mr squared. That gives me q over 2m. So the classical gyromagnetic ratio is just q over 2m. Note that it's independent of r and it's independent of tau. So it doesn't matter what size of ring we chose, we're going to get the same value for the classical gyromagnetic ratio. For an electron, in a quantum electron, the magnetic moment is really a result of the intrinsic angular momentum, that is the spin. But it's not really because of any spinning charge. But we know what that is. We know that mu then is equal to some gyromagnetic ratio for the electron, gamma sub e, times the spin angular momentum. This is not the same as the classical gyromagnetic ratio. It turns out it's 2 times larger than the classical gyromagnetic ratio, roughly 2 times larger due to relativistic theory. So we rewrite the quantum gyromagnetic ratio as minus g sub e, which is this g factor, times e over 2m times the spin angular momentum, or intrinsic angular momentum, s. So this is the quantum magnetic moment for the electron. And g sub e is approximately 2 plus alpha divided by pi, which is 2.002. So the perturbing Hamiltonian is therefore given by h prime, which is the magnetic moment of the electron, which is we calculated here, dotted into the magnetic field that the electron sees from the proton. And because the magnetic field due to the proton is related to the orbital angular momentum of the hydrogen atom, it's just L, and mu is related to the spin angular momentum of the electron, you end up having an interaction that looks like S dot L. And you have all these factors in front, g sub e times e over 2m times 1 over 4 pi epsilon naught times e over mc squared r cubed. If we simplify this a little bit, we get g sub e times e squared over 8 pi epsilon naught times 1 over m squared c squared r cubed s dot L. Now, that's not quite it, because the electron is an accelerating frame of reference. So the Thomas precession correction has to be applied. This means that you can replace g sub e with g sub e minus 1, which results in about 1, because this is 1 over 137 divided by pi, so it's about 1 over 500. So it's really quite small. So we just assume that g is approximately 2. G minus 1 is going to be 1. And so our final spin orbit Hamiltonian is going to be equal to the following. H spin orbit, we will designate SO, H prime SO, is approximately equal to E squared over 8 pi epsilon naught times 1 over m squared c squared r cubed S dot L. So now that we have a Hamiltonian, a perturbing Hamiltonian for the spin-orbit interaction, we take a look at it and we realize that this does not commute with L or S. And so the spin and orbital angular momentum are no longer separately conserved. That is, m sub L and m sub S are not good quantum numbers any longer, because this just doesn't commute with L sub Z, right? Or S sub Z. L sub Z doesn't commute with Lx and Ly, which exist in this. S sub Z doesn't commute with Sx or Sy, which is part of S vector. But the total spin orbit Hamiltonian still does commute with L squared and S squared. And it also commutes with the total angular momentum J equals L plus S, which we showed already in the past. So these quantities are conserved, and the good quantum numbers are then L, S, J, M sub J, and of course N, which is the principal quantum number of the hydrogen atom. So we can use this relationship, the fact that we can rewrite this in terms of J, to recast this interaction S dot L in terms of J, L, and S squared that we can actually calculate. So let's first write down what J squared is. Well, J squared is L plus S dotted into L plus S. That gives us 4 terms. You have L squared plus S squared plus 2L dot S. But this is exactly what we want for our spin orbit Hamiltonian. So if we can solve for L dot S in terms of these other quantities, we should be able to calculate the energy correction, or the expectation value of HS above. Well, when we solve for L dot S, we get 1/2 times J squared minus L squared minus S squared. Right? It's from this term, and this term. And consequently, our spin orbit Hamiltonian can be rewritten as HSO prime is approximately equal to E squared over 8 pi epsilon naught times 1 over m squared c squared r cubed times the quantity 1/2 times J squared minus L squared minus S squared. And that's the spin orbit Hamiltonian that we're dealing with now. We calculated it at S dot L, then we converted the S dot L into J squared minus L squared minus S squared times 1/2. The eigenvalues of L dot S can now be written down, right? So the expectation value of L dot S for any state with quantum numbers J, L, S, M sub J, and N can be written as H bar squared over 2 times the quantity J plus 1 minus L plus 1 minus S plus 1. And so the expectation value of this Hamiltonian starts by taking the expectation value of this term. But you still also get the expectation value of R cubed, 1 over R cubed. And so we have to calculate this expectation value for 1 over R cubed. And we can do that. And similarly to the 1 over R and 1 over R squared that we got for the relativistic Hamiltonian, we have something that looks like this. 1 over L times L plus 1/2 times L plus 1, N cubed, A cubed. And so the spin orbit energy correction, which is just H prime, expectation value of H prime, for a particular hydrogen atom state where you have J, L, S, M sub J, and N as the good quantum numbers, is given by E squared over 8 pi 0, epsilon 0, times 1 over m squared c squared, times h bar squared over 2 from this term here. Then we have J times J plus 1 minus L times L plus 1 minus 3/4 because S is equal to 1/2. So that just gives me minus 3/4. Divided by, down here, L times L plus 1/2 times L plus 1 times N cubed times 8 cubed. And so this is the correction for the spin orbit interaction. So we can rewrite this in terms of E sub n. In terms of E sub n, taking all these constants and bringing them through and replacing that with E sub n squared, I get E sub n squared over mc squared times n times the quantity J times J plus 1 minus L times L plus 1 minus 3/4 over L times L plus 1/2 times L plus 1. And again, you notice that this term is order E sub n squared, just like the relativistic correction. And if we recall the relativistic correction, it looked like E sub R1, the first order energy correction relativistically, is minus E sub n squared over 2mc squared, very similar to the further terms. And then you have 4n over L plus 1/2 minus 3. If you combine these two, and that's done in problem 720, you get the total spin orbit correction simplifies to something, the total fine structure correction, which is the sum of spin orbit and the relativistic corrections, comes out to something relatively simple. It has the same prefactor out here, E sub n squared over 2mc squared. And then this is all multiplied times 3 minus 4n over J plus 1/2. So when you take these two and add them together, you get something very simple at the end. The full energy of the hydrogen atom, including the fine structure, can now be rewritten. So E, as a function of n and j, is equal to minus 13.6 eV, that's E sub n, divided by n squared, times 1 plus alpha squared over n squared, times n over j plus 1/2 minus 3/4. Very simple correction. So the first order, or the 0th order energy, is simply the 13.6 eV divided by n squared. Then you have a correction term which depends on the fine structure squared divided by n squared and times some constants. If we look at what this does, again, looking back here, the energy is negative. The correction is also negative. So the correction tends to lower the energy. And it lowers the energy if this quantity in here is positive, which it normally is. So let's take a look at what happens with the different states. We'll start with the n equals 1 state. N equals 1 state has L equals 0 and S equals 1/2, and so J is equal to 1/2. And remember, the energy depends on J and N. So this energy gets lowered by this term here, and so the energy drops from here to here for the J equals 1/2 side. Now for N equals 2, you have the possibility of having L equals 0 and L equals 1. For L equals 0, you again only have J equals 1/2, and you get a drop. For L equals 1, you can have J equals 3/2 or J equals 1/2. The J equals 1/2 is dropped more. The J equals 3/2 drops a little bit less. You go to the N equals 3, you can now have L equals 2, 1, or 0. For 0, you have 1 state. For 1, you have 2 states, the J equals 3/2 and the J equals 1/2. And for for N equals 2, you again have 2 states, the J equals 5/2 and the J equals 3/2. Again, N equals 4 now has an additional set of states for L equals 3. So let's do some sample calculations. Here is the expression for the energy which is spin orbit corrected, or fine structure corrected. Suppose we have N equals 1, L equals 0, and J equals 1/2. So this is the ground state. So for the ground state, N, which is in red here, is 1. J is 1/2. So I get E of 1 1/2, and N and J, is equal to minus 13.6 divided by 1 squared times 1 plus alpha squared over 1 times the quantity 1 over 1/2 plus 1/2 minus 3/4. So this is 1 minus 3/4. when you put this all together, you get minus 13.6 electron volts times 1 plus alpha squared over 4. Again, this alpha is 1 over 137, roughly. For n equals 2, L equals 0, and J equals 1/2. Similarly, we have everything the same except we have a 2 in here instead of a 1. And now this is 2 over 1. This is alpha squared over 4. And this is minus 13.6 over 4. So you get minus 13.6 eV over 4 times 1 plus 3 alpha squared over 16. So you can see that this is 1/4. This is 3/16, which is less than 1/4. So this is corrected less for the J equals 1/2 and L equals 0. This is corrected a little bit less when n equals 2 than when n equals 1. What about the J equals 3/2? So for the J equals 3/2, we have 2 and 3/2. We have the same prefactor out here. We have 1 times alpha squared over 2 squared. Then we have the quantity 2 over 3/2 plus 1/2, which is equal to 2 minus 3/4. And so this gives us then minus 13.6 over 4 times 1 plus alpha squared over 1/16. So this correction is 3 times smaller than the correction for J equals 0. So the J equals 3/2 gets a smaller correction than the J equals 1/2.